Okay, sorry, just got cut off there. Let's continue. So in the top we have 1, in the bottom we have 1, so we're going to have 1 over 1, and that's just 1. Okay, so for our first limit we see that this is 1. So I encourage you, just go back to the previous bit here, where we substituted different values of n. So go up to, let's say, n equals 10, and just look at the terms. Do you see them approaching 1? And maybe think about how quickly do they approach 1. Okay, so that's just something to think about with that. Okay, so that's example number 1. Let's have a look at another example. Example number 2, we have an is equal to 1 plus 1 over n to the power 3n. Okay, so this one's a bit more complicated than before. We've got this 1 over n in brackets, but we've also got this n term as an exponent. Now, whenever we have things as an exponent, what we would like to do is take the log, because if we take the log, the exponents come down and it makes things easier to work with. So, what we want is the limit of an. That's going to be the limit of this term here. Okay, now we can take the log on both sides. So we can have the log of the limit of an is equal to the log, let's put square brackets, of the limit of this. Okay, now the log, that's a continuous function. Okay, we can just take it as is, you don't need to prove that. So here we can interchange the log and the limit because the log is continuous. So here we can write this as the natural log of the limit of an is equal to, we're going to interchange it, so we're going to have the limit, and then taking the log, we're going to end up with 3n, the natural log of 1 plus 1 over n. Okay, so that is just interchanging the log and the limit. Now, just on the side, we're going to be working with this limit here. And just a note, if we get something like this, what would be helpful when taking the limit is to make this a function of x so that we can use some calculus instead of writing it as n, which is fine because if we write it as a function of x, it still has the same limiting behavior. So we define f of x to be 3x, the natural log of 1 plus 1 over x. So we've replaced n, which is a natural number, with x, which is a real number, but that's fine because when we take the limit, it doesn't matter, right? The natural number going to infinity or x going to infinity, we're going to end up with the same behavior. But the nice thing is, when we've changed it to x, we can now use calculus, which is good. So we're going to take the limit as x goes to infinity of f of x, and this would have the same limit as if we took n going to infinity, where that's the natural number. Okay, so that's the limit. X goes to infinity, 3x, natural log of 1 plus 1 over x. Okay, so just if we imagine x going to infinity, what do we have here? 3x, that's going to go to infinity. This natural log, that's going to go to 0. So we have this indeterminate form of 0 times infinity. Okay, whenever we have indeterminate forms, we should think about L'Hopital's rule. So let's write this in a better form to use L'Hopital's rule. So we have the limit as x goes to infinity, 3 times the natural log of 1 plus 1 over x over 1 over x. Okay, so you've done L'Hopital's rule before. We're just writing it in a better way, where we have type 0 over 0 in determinant form. Okay, so now we can just use L'Hopital's rule. But first, let's take the 3 out. So it will be 3 times the limit as x goes to infinity of 1 over 1 plus 1 over x times minus 1 over x squared for the top part. And then for the bottom part, we have minus 1 over x squared. That's going to cancel. And then if we take the limit as x goes to infinity, 1 over x will go to 0, and we're left with 1. So we just get 3. So the limit of the function is 3, which means the limit of the sequence will also be 3, right? Because they have the same limiting behavior. So the natural log of the limit of an is equal to 3. We want the limit of an, so we can just exponentiate both sides. So we get the limit of an is e to the 3. Okay, which is finite, so this an converges, and it converges to this specific value here. Okay, so please just be warned, we will be using some previous calculus methods, such as limits of functions of x, as well as L'Hopital's rule. Okay, so that will come up. Please be prepared. If you don't remember your L'Hopital's rule or your calculus of single variable functions, please go over that. Okay, that will come up in the section on sequences. Okay, let's have a look at the third example for today. That's going to be an is equal to 4n squared over n plus 2. Again, this is similar to what we had previously for question 1. If you look back at that, if we just substitute infinity, the top part will be infinity, the bottom part will be infinity, we're going to have problems. So what we can do instead is something very similar to what we did in the first case, is we can factor out an n from the top and from the bottom. So here we have a n is equal to 4n over n 1 plus 2 over n. 4n times n. Okay, so we just took out an n from the top and from the bottom. So here we can cancel the n's, and we're left with n at the top, and then 1 plus 2 over n in the bottom. Now when n goes to infinity, this bottom part will go to 1. So that goes to 1, because the 2 over n goes to 0, and the top part, that goes to infinity. So if the top part goes to infinity, and the bottom part just goes to 1, that means the whole thing goes to infinity. Okay, so in the limit, this will be infinity. Okay, so we can write this as the limit an is equal to infinity, and so it diverges. Okay, so remember, if the limit goes to plus infinity or it goes to minus infinity, it diverges. Also, if you have one of those alternating sequences, then it will also diverge. And that's just from the definition of convergence. Okay, so that's just a quick way to work with these problems. All right, we can also have another one similar to this, number 4. So an is equal to, now we're not going to have n squared at the top, we're going to have an n squared at the bottom. So let's say we have n over n squared plus 1. Okay, we want to see what happens with this. Now for this one, we're not going to do this factoring out n, we're going to do another method. Okay, as with a lot of things in maths, there's more than one way to get to the answer. So I'm just going to show you multiple methods to answer these, so you can build up your toolkit of methods to use. Okay, so which one you use is up to you. If it's correct, then I'm happy with that. Okay, for this one, we're going to make a note, and we're going to say that if we look at this bottom part, n squared plus 1, so n squared plus 1, we know is always bigger than n squared. Okay, so that's just a fact. For natural numbers n squared plus 1 is going to be bigger than n squared. Now that doesn't seem like a very important fact, but what we can use is this, we can use this inequality to build up a bound for our sequence over here. Okay, so what do I mean by that? Here we've got n squared plus 1, but in our sequence we have n squared plus 1 in the denominator. So if we take the reciprocal on both sides, this becomes less than 1 over n squared. Now that's very close to what we have here. So what we can do is multiply both sides by n. N is positive, it's never 0, so we don't have any worries with that. So let's just multiply both sides by n. But n over n squared, this is just 1 over n. But we've got our sequence elements an is less than 1 over n. But we know that in the limit, this 1 over n will go to 0. So, and we know that these terms are always positive. So we have 0 is less than this. We can put this less than or equal to, that doesn't change this. So we have 0 is less than or equal to our sequence term, which is less than or equal to 1 over n. But we know that 1 over n goes to 0. This goes to 0 in the limit. On the right it goes to 0, on the left it goes to 0. So by the squeeze theorem, we have that our sequence elements also go to 0. So we can write here that the limit of an is 0. Okay, so this is the full working that you need to show this, but a very quick way, just to check your answer, is if we look at the exponent in the top, we see that the exponent is 1. The biggest exponent in the denominator is 2. So the denominator has a bigger exponent, so you can think of this as the denominator being larger than the numerator. And in the limit, when n gets very, very large, n squared is much bigger than 1. So we can ignore the 1. So this the numerator is n to the 1. The denominator is just n squared, again in the limit. So n over n squared, that's 1 over n. 1 over n goes to 0, so our sequence also goes to 0. Okay, so that's just a quick recap of the thinking. Please actually show the working when you do these. Okay, last one for today, number 5. We're going to have the limit of the square root of 9 plus n squared over 4n squared. Okay, now the square root we know is a continuous function. So we've got the limit of a function of a sequence. We can interchange the function and the limit. So interchanging those two, we get the limit of 9 plus n squared over 4n squared. We can simplify this, so this will be the square root of the limit 9 over 4n squared plus n squared over 4n squared, that's just a quarter. Now if we take the limit, this n squared is going to go to infinity, so 9 over infinity, that's going to go to 0. That's going to go to 0. The 1/4, that's not affected, so we just end up with the square root of a quarter, but that's just 1/2. Okay, so here we used the fact that the square root is continuous, so we can interchange the limit, and it makes it very easy to solve. Okay, so that's going to be it for today. We will continue with limits, limit properties, limits, sequences, sequence properties, bounded sequences, and some more examples in the next lecture. Okay, so I'll see you there.